So today we'll be studying direct torque control of induction motor drives. Uh, so we have studied the scalar control strategies associated with induction motor drives, and we have also studied the vector control strategies associated with induction motor drives. So in scalar control strategies, the thing is that we only control the magnitude of the voltage and frequency, the control parameters. We only control the magnitude of those control parameters in order to control the speed or torque of the induction motor. Whereas in case of vector control strategy, we control the magnitude as well as the phase for control of speed and torque. Now there's a third type of strategy that's somewhere in between scalar control strategy and a vector control strategy. Uh, it's also in books you'll see it's classified as an advanced scalar control strategy. Fine. Advanced scalar control strategy. It's also known as it's known popularly by the name direct torque control. It's also known as wherever you will find the term direct torque and flux control, that also refers to DTC only, and also known as uh, direct self control. So direct torque control, as the name suggests, as the name indicates itself, it is the direct control of the torque and the stator flux of the induction motor. Uh, so by the help of space vector modulation strategies or by the help of vector control strategy, vector selection methods, we can actually control the torque as well as the flux of the induction motor directly using the direct torque control strategy. In case of vector control strategy or in scalar control strategy, what we actually do is we control the speed in order to control the torque. We have the value, we take the measurements of speed, and using that measurements of speed, we compare with the reference value of speed in order to get a reference value of torque. We do not measure torque or flux directly in case of vector control strategies and control them directly. But in case of direct torque control, we'll be directly measuring the torque, we'll be directly measuring the flux and comparing them with their respective uh, reference vectors so as to control the induction motors torque oblique speed and flux. Fine. So the basic block diagram of a direct torque control. So this is a block diagram of a direct torque control. So using the motor's parameters, what we are doing is we are calculating the values of torque and stator flux. Fine. So we are calculating the motor's torque and we are calculating the motor's stator flux from the from some control parameters, and that torque is compared with some reference value of torque, and similarly that flux is compared with some reference value of flux, uh, and using a switching table and voltage space vector modulation, we are able to generate pulses for the inverter that feeds back the motor. Fine. So this portion of control, that is controlling the speed oblique, that's controlling the speed, is no longer required in is not a necessary part of the direct torque control strategy. Fine. We can directly measure the torque, compare it with the reference value of torque. We can directly measure the flux and compare it with the reference value of flux using control strategies. Here the control strategy involves use of hysteresis band and use of space vector modulation for generation of pulses for the inverter. Now the logic that in data control, what we do is the switching logic for the hysteresis controller here is it will either take up, the output of this will be either positive, this value h, that's the control parameter here, that will be either 1, or h psi will be -1. H psi will be +1 if this error, the error between the measured value of flux and the reference value of flux, if it is positive, and if this error is negative, H psi will take -1 as the value. So accordingly, the information fed to this table here is H psi is either +1 or H psi is -1 depending upon the value of error. While as far as this control parameter is concerned here, ht, it will be either 1, it will be 0, or it will be -1 for et greater than 0, for et equal to 0, and et less than 0. So using this hysteresis band, what we can do is we can obtain the values of h psi and ht. H psi will be a 2 level. It will only have a 2 level fluctuation, while as HTE will also involve the vector, will also consist of 0 as the output. It will be a 3 level, uh, 3 levels of digital output will come from the torque control loop. Fine. From the flux control loop, only 2 levels of digital output will be available, whereas from the torque control loop, 3 levels of digital output will be available. As far as these equations are concerned here, this we can we can either use torque sensors for measurement of torque, or we can use estimators observers for estimating the values of torque. So if you are using some estimation block, so in that case we'll be using this equation here for calculation of torque, and this equation here for calculation of flux, or we can use directly flux sensors and torque sensors for generation of torque and measured values of torque and flux. Now, as far as flux is concerned, flux sensors are very poorly designed. So most of the cases you will see that flux is not measured using flux sensors. It is estimated using uh, the known values of voltage and currents. So now from the torque control loop, what we have obtained is we have obtained 3 levels of digital output, and from the flux control loop, we have obtained 2 levels of digital output. Now, using this knowledge, what the vector modulation scheme will do. So, what we have obtained from the torque control loop is 3 values of digital output: 1, 0, and -1. And from flux control loop, we have obtained 1 and -1. So, using these knowledge, if both the values are 1 and 1, 1 and 0, 1 and -1, all these 6 possible conditions, what we have designed is that the output pulses will be either V2, V3, V4, V5, V6. Fine. So these outputs here, they'll be referred to as by Vn. Now what Vn signifies here is, So if H psi and HTE both are 1, what we'll be having is that the selection will be in such a fashion that these vector controls, these possible switchings will take place. And what are these switchings? They are depicted here in this diagram. This is the space vector modulation. Space vector modulation basically shows us the orientation of the vectors field in a three-dimensional space. Fine, and instead of consisting of a normal six logics, it consists of eight switching logics. Okay, so we have actually, for example, we have a three-phase inverter. S1, S3, S5, S2, S6, S4. Fine. So we know what will be the switching logic of this inverter is 1, 2, 3 will be on, 2, 3, 4 will be on, 3, 4, 5 will be on, 4, 5, 6 will be on, 5, 6, 1, 6, 1, 2, 1, 2, 3. So the possible switching states using a normal pulse width modulation system is that either switch 1, 2, 3 will be on, either switch 2, 3, 4 will be on, 3, 4, 5 will be on, 4, 5, 6 will be on, 5, 6, 1 will be on, 6, 1, 2 will be on. So these are the possible six switching states. But in case of space vector modulation, we have a third, we have two non-reference values, in which case 1, 3, 5 will be one switching state. That means switch 1, 3, and 5, the upper leg switch will be on. We understand that with all the upper leg switch on, the inverter will not actually be functioning. And similarly, we'll have 264, the normal will have the bottom three switch functioning at the same time. So these are represented using these vector spaces. So V1 represents a vector space 1, 0, 0. 1, 0, 0 simply means that the upper switch will have a configuration of 1, 0, and 0. That means switch 1 will be on, switch 3 will be off. If switch 3 is off, that means switch 6 will be on. And if switch 5 is off, that means switch 2 will be on. Okay, so the 1, 0, 0 basically signifies the switch 1, 6, and 2 are on. That means 6, 1, 2 switching logic state. Fine. As a V2, this vector voltage vector refers to condition 110. 110 means 1, 3 are on and 2 is on. V3 refers to 010, V4 refers to 011, V5 refers to 001, V6 refers to 101. Fine. So all these switching states are defined using this vector space, and there are two perpendicular vectors V0, V0 and V7. So V0 refers to 000 and V7 refers to 111. So they will not actually be producing any output. So since the magnitude of output using those vectors will be 0, so they are not actually shown in this two-dimensional space, but they are perpendicular to this two-dimensional space, having a magnitude of 0. So accordingly, using now this logic, if H psi and HT are on, we can have the voltage vector V2. That means correspondingly जो हमारे switching states होंगे, हमारे जो switch होंगे, either we'll have V1 on, we'll have either V2 on, we'll have either V3. The voltage vector will be V3, either it will be V4. So these, depending upon in which sector, these refer here to the sectors. Sector basically refers to, in this diagram, there are 6 sectors. 0 to 60 degrees refers to one sector, 60 degrees to 120 refers to another sector. So depending upon one, हमारा जो फ्लक्स कंट्रोल लूप से क्या आउटपुट आ रहा है, टॉर्क कंट्रोल लूप से क्या आउटपुट आ रहा है अकॉर्डिंगली, एंड ऑल्सो हमारा जो अभी फेज है वो कितना है. फेज will actually define what is the sector in which our voltage vector is presently, हमारा वोल्टेज वेक्टर किस स्पेस में है अभी. फाइन. डिपेंडिंग अपॉन दैट सेक्टर selection and depending upon the magnitude of H psi and HT, we can determine now whether our output is V2, whether our output is V3, whether our output is V4, whether it is V5, V6, V1, or if it is V0 or V7. ठीक है. So we have now 8 switching states: V0, V1, V2, V3, V4, V5, V6, and V7. V1 is this, V2 हमारा ये हो गया, V2 हमारा हो गया 1 3 1 3 and 2. That means this V2, V3, V4, V5, V6. ठीक है. So V1 will refer to these three switches will be on. Fine. 6, 1 and 2. 1 हमारा जो मैग्नीट्यूड ऑफ एच साई है और एच टी है वो क्या है, और दूसरा हमारा जो फेज है अभी वो किस सेक्टर में लोकेटेड है. ठीक है. दिस टू डायमेंशनल स्पेस, इट्स अ 360 डिग्री स्पेस. Fine. Divided into 6 sectors. This is S1, this is S2, S3, S4. So 0 to 60 degree is first sector, 60 degrees to 120 is second sector. अब एक तो हमें एच साई और एच टी का भी वैल्यू पता होना चाहिए और दूसरा हमें सेक्टर भी पता होना चाहिए कि हमारा अब फेज कहाँ पे लोकेटेड है. Now, depending upon all these three conditions, we can now determine what our switching pulse pattern will be for the induction motor. Okay? So this vector will be continuously rotating, so sectors will keep on changing. So even if H psi and HT, they are both fixed at 1 and 1, हमारे जो voltage pulses होंगी, they will change from V2 to V1 in this fashion. That means हमारी जो switching pulses होंगी, they will change in this fashion. So accordingly, we'll be able to obtain the control of torque and flux in this case. Fine. So the torque control loop, it's a 3 digital output control, and the flux control loop, it's a 2 digital control. And in this diagram you can see also ये जो सेक्टर कहाँ से मिलेगा हमें, थीटा कहाँ से मिलेगा हमें, that will be also calculated using this equation. हमारा जो phase है अभी, हमारा जो कौन सा सेक्टर होगा अभी हमारा, that will depend upon the phase. Accordingly we can switch, we can see whether our sector is 1 2 3 4 or 5 or 6. Depending upon the sector and depending upon H psi and HT, we will be able to determine what will be the pulse pattern for the induction motor. Okay? So you have to look into 3 conditions. You have to check the value of H psi, whether it's +1 or -1. You have to check HT, whether it's +1, 0 or -1. And you have to see the phase. Depending upon the phase, you have to see whether it is sector 1, sector 2, sector 3, sector 4, sector 5, sector or sector 6. ठीक है. हमारा जो एंगल है, whether it is between 0 to 60, whether it is 60 to 120, 120 to 180, 180 to 240, 240 to 300, 300 to 360, ये जिस सेक्टर में होगा वो हमें देखना है. डिपेंडिंग अपॉन once we get the reading of all these 3 conditions, we can say what will be the voltage vector output. ठीक है. voltage vector basically defines हमारा जो 3 फेज इन्वर्टर है उसके कौन से स्विच अभी ऑन होंगे. ठीक है. So as I said to you, there are normal 6 operating conditions and 2 non-operating conditions. जो हमारे नॉर्मल 6 ऑपरेटिंग कंडीशन है जो आपको ऑलरेडी 3 फेज इन्वर्टर से पता है, दे आर 1 2 3 2 3 4 3 4 5 4 5 6 5 6 1 6 1 2. That means these combination of switches can be on at a particular time, and there are 2 non reference that will not actually produce any output. They are When 1, 3, and 5 they are all on, or when 2, 6, and 4 these three switches are on. Fine. So in this two-dimensional space, only six vectors are shown, while as the two non-reference vectors, that is V naught and V7, they are perpendicular to this reference frame and they have a magnitude of 0. Because with all the upper legs switched on or all the lower legs switched on, the inverter will actually not be able to produce any output. So these three logics will govern our voltage vector output. That will actually tell us which switch of the inverter will be on, and accordingly, depending upon the pulse patterns, we'll have that much amount of voltage fed to the inverter that will result in control of speed oblique torque of the induction motor. Right. So this is the basic control strategy of the DTC, direct torque control strategy, without going into much details. So, with respect to vector control strategies, what are how we can compare it with respect to vector control strategy or scalar control strategy? Uh, in case of vector control strategy, we saw that we compare the measured values of current with the reference values of current for uh, determination of pulses using the hysteresis current controller. So we need the feedback of current in case of vector control strategy, but in case of DTC, we do not need the feedback current. We do not need the current to be fed back into the system for any control. Right? We do not use the traditional PWM strategies. We are using the modern space vector pulse width modulation strategy, which consists of 8 switching logics, not just 6 switching logics. Vector transformation is not necessary. That means ABC to DQ transformation is not necessary. In case we are using the estimator, we need PSIDS, PSIQS, IQS, IDS. In case we are not using an estimator, in case we are simply using sensors for flux and torque measurement, in that case we do not need this estimator and we can directly measure the values of torque and flux. So vector transformation is not necessary. That means ABC to DQ transformation is not necessary in this case. So these are some of the advantages with the direct torque control that compared with the vector control strategy. We do not need the current control loop for feedback. We are not employing traditional PWM strategies. We are applying space vector pulse width modulation. With space vector pulse width modulation, our THD profile, our control strategy is much more better as compared to the traditional schemes. We do not need vector transformation, and at the same time, we are able to control torque and flux independently. Torque and flux control will still be independent in case of direct torque control strategy. They are not dependent upon each other. And but the disadvantage with this is we are using hysteresis uh, band for control of torque and flux. Uh, we are not we are not employing current control strategy, but we are employing hysteresis band for control of torque and flux. these two bands. So because of the use of these two hysteresis bands, what happens is hysteresis band offers non-linearity in the system. It results in variable switching frequency. Fine. So hysteresis band, which that's an associated problem with hysteresis band. It will cause variable switching frequency, just as in case of HCC. So this is about the data control of induction motor drives. Compared with vector control strategies as well as scalar control strategies. The advantage of scalar control strategy is that we have a decoupled torque, flux and torque control. We are not, flux and torque control will not be dependent on each other in this case, and we can control both flux as well as torque at the same time. Compared with vector control strategy, the advantage is that we do not need to go for the transformation. We do not need to go for ABC to TQ transformation for control of flux and torque. So DTC is offering DTC compared to vector control and scalar control strategies both is offering much more favorable results as recently with more and more control, more and more research going into this with the use of uh, better control strategies, predictive controllers, etc. There has been a lot of improvement in DTC as well. So it's offering much more. It's promising much better results as compared to both vector control strategies as well as scalar control strategies. Fine. So there is still an ambiguity as to whether it's a vector control strategy or whether it's a scalar control strategy, because we are not directly controlling phase, but somewhat we are actually going for vector control as well. We are going for phase control through the space vector modulation strategy in itself employs the phase control. Okay? Depending upon phase, we are switching. We are हमारा जो phase होगा यहाँ से that will actually determine the sector in which we are operating. So there is some control of phase required in this strategy, but we are not directly employing that phase control anywhere. So that actually makes it an ambiguous. There's an ambiguity whether it's a scalar control strategy or a vector control strategy. So what the modern term suggests is it's an advanced scalar control strategy. So they do not say it's a scalar control strategy, they just say it's an advanced scalar control strategy. So that's all for induction motor drives. We have studied the sensorless control, we have studied scalar control, vector control, and dipole control. So we'll be taking up synchronous motor control from the next session. Fine.